Okay, so hello everyone and welcome to our 13th Inspiration Exchange session. Today's topic is how we can make ML models as robust and useful as possible. My name is Nick Maxfield. I handle the Schaar Lab's communications. I'm joined today by Mihaela van der Schaar, of course, as well as by three of our PhD students, Boris, Kamilė, and Trent, who will be giving presentations and also be having a discussion with you later on in the session, as I'll explain in just a minute. So first, just to give you an idea of what to expect from today's session, our ongoing aim with Inspiration Exchange, as always, is to share and explore the breadth of topics in machine learning for healthcare and to generate new ideas for future research projects. In our previous session, we took another look at ITE inference, or individualized treatment effect inference, which is one of our mainstay or core research topics, with a particular focus that time on what's around the corner. And we introduced some new approaches and discussed them with you as well. And if you haven't seen that session yet, it is available on our YouTube channel, or you can find it on our website as well. But this time we're changing things up in a couple of different ways. So firstly, we're looking at quite an open-ended topic, which is making ML models as useful and robust as possible. And to do this, we're kind of focusing on three particular areas. One is fair synthetic data, one is uncertainty estimation, and one is missing data imputation. And the other way we're changing things up a little bit is really, this time we actually want to ask you a lot of questions. So we'll do this in the form of both polls and kind of open-ended discussions where we will hopefully hear from you about your own opinions and experiences. So to explain this a little bit, because it is a bit of a change in format from our usual format, often we do kind of one half presentations, one half Q&A or discussion. This time, everything will be a little bit more mixed in together. But one thing I'd like to ask you to be ready to do is to raise your hands in order to share your opinions or experiences. I don't mean that right now, but I mean, there should be a sort of function in Zoom under reactions where you can click reactions and raise your hand. I can see someone's already worked it out. Again, no need to do that just yet though. So basically, time-wise, to break this down a little bit, after my introduction, Mihaela will just say a couple quick words, and then we will go into the first of our presentations, which is on fair synthetic data, which is given by Boris. And after his presentation, we'll do a quick poll and then discuss basically the answer that you gave in the poll. So we'll ask a few of you to raise your hands based on the answer you gave, and we will choose maybe one or two of you to answer. And then we'll kind of go through the same, actually, well, Kamilė's is a little different because we won't do a poll. We'll do one open-ended question to kick things off and then kind of an open-ended question at the end of Kamilė's. And our third presentation will be by Trent Kyono, and we will do a poll at the beginning of that one and then discuss the answers you gave in the poll at the end of Trent's presentation. And then we'll have a quick sort of 5-minute or so wrap-up discussion where we try and tie together these three topics with another kind of raising hands open discussion. And hopefully, if everything goes according to plan, time-wise, we will wrap up at about 5 o'clock. So, oh yeah, and one thing I wanted to just draw attention to before we go into Mihaela's quick introduction is that we are recruiting for fully funded PhD positions starting in 2022. If you are interested, please visit our website and click the big Join Us button that you'll see on the right. And then you can sort of fill in your details on a form that is right on that page. Anyway, without further ado, I'd like to hand over to Mihaela just to kind of give a couple words of welcome before we then move on to Boris.
Thank you, Nick, very much. And thank you, everyone, for joining us. I'm really excited that we are going to discuss this topic of robust machine learning. And here we are focusing less, like we have done in the past, in just building analytics, whether it's risk prediction models or treatment effect estimation, and rather look at the inputs, which are really what type of data we can have. Can we have synthetic data that is more fair than real data? Can we deal with missing data imputation? As well as the, let's say, outcome of the models that are trained on this data. Can we say something about how uncertain we are in the predictions we make, or what certain we are, and when can we trust the model and when we cannot? And these are just some of the many topics that are involved in building more robust machine learning methods. And we believe that this is a very big and important agenda in machine learning for healthcare. So we are very interested to hear your opinions And I really hope that you are going to engage with Kamilė, Boris, and Trent in this. Thank you.
Lovely, thanks very much. So first up, as I mentioned, we have Boris, who will be talking about fair synthetic data. So at the end of Boris's presentation, we'll be doing a poll, and then we're going to kind of ask you a couple of questions based on the what you answered in that poll. But Boris, whenever you're ready, please go ahead and share your screen.
Thank you, Nick. Let me just share screen. So I'm going to talk about synthetic data. And the problem, as I discussed, is that in the healthcare setting, there are privacy concerns. And because of these privacy concerns, it's often very hard to share your data with machine learning community. This leads to a lack of high quality healthcare data, which in turn impedes machine learning research in healthcare. So how do we solve this? We saw two approaches: the de-identifying data, which means to remove any personal identifiers. But as I explained before, this does not actually guarantee privacy. So this should be discouraged. And the other option is to create synthetic data, which is data created entirely from scratch using machine learning models. So in some sense, we need machine learning models to create this synthetic data so that we can do more machine learning. So why synthetic data? For one, synthetic data can be used to develop analytics. So you can publish your data and then other people can do research based on this data. Related to this, it also facilitates the reproducibility of clinical studies and analyses. So if you do research and you publish an article on it, it would be quite nice if other people can reproduce those analyses. A third reason to want synthetic data is to augment the data. In some cases, the real data itself might not be optimal. So, for example, in some clinical studies, there might be very few rare diseases, or there might be underrepresented patient subgroups. If you learn what the distribution looks like, you can then generate additional data for these underrepresented groups, such that the data set is more balanced. And then at last, it also increases robustness and adaptability of machine learning models. So, for example, consider that that there's multiple hospitals and they each use their own data to create a model to predict some disease. Well, maybe it is better if they would use not just their own data, but also synthetic data from the other hospitals so that their model is more robust. Okay, so these are multiple reasons to want synthetic data. Today, we're going to look at another reason, namely to generate fair data based on unfair data. Let me motivate this a bit more. So the problem is unfair real data can lead to unfair downstream predictions. Consider if you have unfair data and then train a prediction model, this will of course lead to unfair predictions. And then the aim is, can we create something in the middle? So can we create a synthetic data set that is fair so that we can use it to train a prediction model so that we can get fair predictions on real data? Well, this is the aim of DCAP, a method that we proposed a while ago and are presenting next week at NeurIPS, called DCAP Generating Fair Synthetic Data Using Causally Aware Generative Networks. This was a collaboration with Trent Kyono, Jeroen Bergvoet, and Mihaela. So what are the challenges here? For one, there are many different notions of fairness. So depending on your definition of what is fair, you might need to remove different kinds of bias. Secondly, if we look at this example below, where we have a graphical system, so for example, age leads to the number of years employed, and the years employed leads to your credit score, or etc., etc. If we now, for example, remove variables, in this case, the protected attribute, so something we don't actually want the model to use, ethnicity, for example, if we remove this from the model, actually, we still have indirect bias via the merit variable in this case. So just removing this variable from our data set does not suffice because we still have this indirect bias. So one of the challenges is to guarantee fairness of a downstream model at the data level. So if you were a data holder, you would want to be able to publish your data with the guarantee that if someone would just agnostically train a prediction model based on your data, that they will get fair predictions. And this is quite challenging. And in the end, just having fairness is of course not enough. We still need to preserve the data utility. So how does DCAP achieve this? these things. DCAF uses a causal perspective, like we saw in the graph before. And this causal perspective provides us with an intuitive guideline to achieving different fairness notions. And it also provides us with a way to give guarantees for a given downstream setting. Additionally, DCAF's devising is effective. As I will show later, we make local changes to the distribution, which means that globally there's not that much that changes between our synthetic data distribution and our real data distribution. So the quality of the data is preserved better. So how does DCAF work? It's pretty simple and just consists of 4 steps. The first step is, well, given this graphical model, which we assume we know, in this figure we see that A is the protected attribute, let's say gender, which leads to B, leads to C, and then Y is whatever we want to predict in the downstream case. So for example, someone's salary. So the 4 steps are as follows. For one, we train a generative model based on the causal structure of the data. We could, for example, use a GAN structure for this. So we learn how to generate A, that's the first variable. Then we learn how to generate variable B based on A, and we basically iterate. So then we learn C, we learn D, we learn Y. Subsequently, if we've learned this, we've of course learned a model that is biased because the data is biased. But then we take the actual graphical system and we remove the edges that we don't want. And this will depend on the definition of fairness that we use. For example, if we don't allow any direct discrimination, we will just remove the error from A to Y. But in some cases, we might say, well, in fact, we don't allow any indirect discrimination either. Then we need to remove the edges from B to Y or from C to Y. And there's more definitions of fairness that might give different choices. So then we remove the edges and we use the same model that we had before, but now with these edges removed. And then the 4th step is to actually generate synthetic data. So here I'm showing some results. I won't go into detail, but we can see that DCAF, in contrast to other methods, preserves data quality pretty well, while also guaranteeing the different definitions of fairness. And here we see that DCAF, given 2 different definitions, here the FTU and DP, which basically corresponds to direct discrimination and indirect discrimination, we can make sure that if we want no indirect discrimination, we actually get indirect discrimination. And so we can choose which fairness notion we want to achieve. And here's some more results, but I think I'll skip through it. So in conclusion, DCAF can generate fair synthetic data based on unfair real data. It is compatible with different definitions of fairness, and we can give guarantees for the downstream model of fairness. And in the end, we saw that also the data quality is preserved. So now back to you. So basically, I'm very interested to know how you use synthetic data and whether fairness is also an issue for you. So I'll be discussing 3 questions. I'll just put them on here for now. So the first one is, are you using synthetic data or thinking about doing so, and with what purpose? The second one is, are there any characteristics specific to your data that will make generating data particularly challenging? And then the third one, is fairness an issue in the data you own? Are there known biases in your data? Nick, oh, perfect.
So you should hopefully see on your screen now the first poll we've done in Inspiration Exchange. So basically the 3 questions Boris just asked should be available for you to answer. So please, I guess I'll run this poll for maybe like a minute or so. I see some answers already coming in, which is fantastic. So please go through all 3 of Boris's questions, put your answers in, and then I think Boris will probably pick people who gave certain answers to certain questions, right? And you want to hear from them in particular, I assume. So maybe people who replied no to a certain question, yes to a certain other question. So we'll keep this running for a few more minutes. Sorry, a few more seconds, I guess. Probably don't have the luxury of a few more minutes. And let's see, I guess we can already start some people raising their hands as well. So I think, Boris, your first question was to people who answered yes. I think you wanted to know, basically, can they tell you what purpose they've been using synthetic data for, or are thinking about using synthetic data for, I guess. So if anyone who has answered already using or is considering using, if you want to raise your hand, and please just basically tell us why. So I think we have Diyuan. So Diyuan, if you want to go ahead. I'll run the poll for just a few more seconds, by the way, and then I'll show everyone the results.
All right. Yes, thanks. I'm considering using synthetic data in my work. So in our study, we have the metadata, which is collected from a few hundreds of patients, and it's always tricky to get enough data from enough patients to cover the variabilities. And in our research, the data is very noisy, so with noisy labels. And we were thinking about how to generate more data that representing different characteristics from different patients, as well as different characteristics of the data itself. And the data is magnetic resonance spectroscopy. Yeah.
That sounds really cool. Nice. And so so you're basically trying to balance your data then. So trying to generate additional data for.
Boris, you are no longer on camera.
Yes, sorry, I switched it off briefly. I'm currently in a room where I'm just for the internet. So anyways, sorry, but yeah, so you're trying to balance your data.
Yes, basically covering more diversity of the patients, because sometimes the interpatient variability plays a huge role.
Interesting, interesting. And what kind of model are you using?
So far, we are using convolutional network, because it's just data array for each data points, each spectrum. So we are using convolutional networks.
Cool, cool. I think let's go to another person. So maybe Radhika Dua.
Yeah, actually, I used synthetic data because in real world distribution of data changes from one hospital to another due to several factors. One is because of different setup, like different lightning conditions. So data collected from different hospital differs. And to reflect that, I just use I created a simple synthetic data where I changed the brightness of the data, brightness of specifically chest X-ray images. And then I tested my model on that shifted data. So this was done just to reflect the real world scenario.
Ah, okay. So it's not, you're not necessarily learning how to change the data, but you're putting some a priori knowledge in it. So by changing the brightness yourself. Yeah,
right.
Yeah, okay. Yeah. Okay.
Boris, do you want to call on someone who answered a different question, either because of the kind of poll results here, or just because maybe there's another question you want to hear from someone about?
Yeah, I would also be interested to see the second one. I'm not sure how the poll went. Maybe Nick, you can choose someone. So the second question, what kind of characteristics? Oh, sorry.
Yep. So the poll results, I think most of you should be able to see them. If you aren't, then sorry about that. But the poll results, the second question, the most common answer was presence of missing values. As a reason generating synthetic data would be particularly challenging. That's kind of interesting because I guess also we have Trent up next, but the second most chosen was high dimensional, the third being multiple modalities.
Yeah, okay. Oh, that's an interesting result. And then the third one, fairness. Could you briefly summarize the result?
Yep.
Nick?
So a plurality of people answered that fairness is an issue in the data they own. 42% answered.
Could someone who answered yes there raise their hand, because I'd be interested to hear an example.
There are at least 11 of you, so
I
don't see any raised hands.
Maybe
that's okay. I don't think that's a problem. And I guess maybe anyway, in the interest of catching up a little bit, if you're okay with it and you don't have any follow-ups,
no,
then
I'll just briefly mention, if you are interested in synthetic data, we have a lot of information on our site. It will be easy to follow advanced research pillars. So please have a look there. Okay, thank you.
So let me just do a quick intro to Kamilė's presentation as well. 1 second. Okay, yep. So Kamilė is one of our PhD students, and she'll be giving a short presentation on uncertainty estimation. But I believe, Kamilė, actually, you want to start with a kind of a slightly open-ended question for our audience as well as.
Yes, so I could start presenting, and then my question is actually in the presentation, so I could.
Okay, so we kind of stop partway through, you ask your question, and then some people raise their hands, you call on them, and that's about right. Okay, brilliant.
Great. So I'll be presenting something related to uncertainty estimation. So it's my most recent work, but the discussion I think would be a bit broader. It's regarding just uncertainty estimation. And I wanted to start with a question to all of you. How does uncertainty appear in your medical machine learning applications? And how do you estimate it?
So I guess this would be a good point if anyone wants to raise their hands, and basically if you have any thoughts on Kamilė's question, please just raise your hand. Again, click reactions, raise hand. And we'd like to call on one or two of you. Okay, so we have a hand raised already. I think it's by Moen. So Moen, if you want to go ahead and.
Hi, can you hear me clearly?
Yes, we can.
Okay, so one of the applications that we encounter is that we usually have some data from some hospital, and we do the machine learning methods on them. We develop and prepare our predictive models. But we do have a problem with extending the results to other hospitals. This is my experience.
So the difference in domains and so when you transfer to a different environment, probably.
Exactly. It seems that patients from one hospital to another hospital are a bit biased. And yeah, this is a problem that we have currently.
Very, very important point. Thank you so much for this. I've seen Joshua raise their hand.
Yep.
Next.
So please go ahead, Josh.
Hi. Yeah. So I think there's uncertainty inherent in the medical domain. For example, diagnoses. So a clinician doesn't know exactly. Like, although a doctor will say, "We think you've got this," they don't know what you've got, and that can kind of all that uncertainty can feed into your training and stuff.
Yeah, so there are like different things. So like what the first point that was mentioned, that you kind of learn the model, then there's uncertainty in applying it to a different setting. And here it's also uncertainty in the prediction itself within the same population. So there's already two types of uncertainty. I see Radhika also raised a hand. Would you like to say something?
Yeah, I would like to add that when the age of patient changes, then also there is uncertainty. So if a model is trained on, say, 26 years old, and if we test on other age groups, so we would have some uncertainty.
Yeah, and probably even for the same patient, because like if let's say you are 26 and then you make a prediction on one patient, and then like a month later, because that patient has already changed, yeah, so the same prediction is already invalid, even though the person is the same.
Yeah, exactly. And other scenario could be when new labels come. So for example, COVID never existed before, but your model is trained like say 2 years back, and now COVID is there. So model won't be able to predict, and we cannot guarantee about its predictions.
All very interesting points. Like, but like due to the time, like could I also ask, like, does anyone have opinions like about how do you estimate that? So for all those types of uncertainty, how do you try to address that? Have you ever done something? Have you heard of any methods that could do it? What are your thoughts?
So Hussein, I don't know if your hand was up because you have an answer to the latter question. If you do, please go ahead.
Actually, I encountered with a real-time uncertainty problem because of the COVID situation. It's related to, I trained for a Samsung company, I trained a smart HVAC system. And there is a rule in Korea that there is a 30% ventilation because of the COVID, and before there was a ratio was decreased. And because of the COVID situation, there is a proper regulation on the ventilation system. So the whole data set is changed very dramatically in recently. So we trained our model again in an incremental way, so to reduce the uncertainty. And also we compare our prediction and the real-time values in our forecasting, time series forecasting. So if the distance between them is increased, the Euclidean distance or some other type of error rate increases, and we have a proper threshold on them, and then we solve some problems related to it.
So you mean the forecast when what exactly did change?
The thing is, we trained the data and we calculated the loss, the error, the total loss, the training loss and the validation loss and the test loss, of course. And then we created the threshold, proper threshold for it. And in a real time, there is a real time values and our predicted values in a forecasting way. And then we compare both timestamp. And then if the distance between both timestamp increases, then and it increase, it's above that threshold, then we say that there is a problem and the uncertainty is increased now. So we have to train our model again on an incremental way.
Right. So you see when there's a difference between your how the model performs and how it is expected to perform, when there's a thank you so much for all those answers. I believe there's not much time, but like very, very interesting discussion so far. And I would like to present like a method related to what has just been mentioned. So my problem that I explored in my thesis just a few months ago was exactly on time series forecasting, actually. So it's like data over time. And then we try to predict like things in the future. And this is actually important, also especially in the clinical settings, because as was also mentioned in the discussions, patients change over time. A patient is not just a current snapshot, they are just actually a history of records, and their optimal treatment might depend on that history and not just what your current state is. And so I focused on the forecasting, and also in my case, like a point prediction of just like a single time series trajectory that is most likely is not enough. Because if that motivates the doctor's decision to prescribe a drug or something, you do not just want the most likely outcome, but you might also want to care about the possible, very unlikely, but very adverse outcomes that you really want to avoid. So if the drug has a side effect that kills the patient, you would rather, not prescribe that drug to save, to not kill the patient, so and so on. So, and you also want this model to perform with some guaranteed properties. You just don't want the model to, work most of the time, but sometimes not work. You actually want to know how certain it can actually be, in theory, guaranteed, so that you can use that knowledge to weigh your decisions appropriately. And this is a formalism of the problem. So we have a D-dimensional multi-horizon forecast. So that multi-horizon means that you predict many steps in advance. And we want to, for each of the steps in the horizon. We want to obtain the prediction intervals, lower and upper, so that the true values contained within that interval with a certain probability, or that the error rate is bounded to a certain level alpha, which I call it here. So we want the entire time series to be contained within those intervals with, let's say, at least 95% probability, which would mean that error rate is 5%. And so far, there have been multiple methods to do that. So most frequent ones are Bayesian recurrent neural networks, where in the neural network, every weight is parameterized by distribution, and then you try to estimate the distributions. And then when you make a prediction, you kind of sample from that neural network, and you get like a set of predictions that kind of give you an estimate of uncertainty. Then there are quantile recurrent neural networks, which actually directly are trained to predict lower and upper quantiles directly. So when you apply the mean squared error in your standard point prediction setting, when you apply the mean squared error, it actually trains the model to predict the median value. So you adjust that to a bit of a different loss. Instead of mean squared error, sorry, not the mean squared error, actually mean absolute error. So you change the mean absolute error to a different type of error, which is very similar, called the pinball loss. And then that predicts like the different quantiles, which you can then use. So then the predicted values like should be between like 10th and 90th quantile, let's say. And you can use that, but the problem with this is that it requires like a lot of data to train those quantiles correctly. Then there are certain state-based models which actually use like things like Markov chains to represent the uncertainty. And there was also a recent method of blockwise jackknife RNNs developed by Ahmed Allah from our lab, which was based on frequentist resampling of the data set in order to obtain the prediction intervals, because the resample data sets would train a slightly different model. And then again, you can run all those models and then get different answers which represent your uncertainty. And the challenges of these solutions, as I've mentioned, is that the architectures are usually built in. So in Bayesian RNNs, you kind of have to double the number of parameters, because every weight in the neural network is now replaced by a distribution, which is, let's say, parameterized by a mean and variance, and that kind of has to be built in. So you can't use your original model that you would want to use. You have to change it, which means that it might change its performance. Then there are sample complexities. So for example, when you train this quantile RNN, which tries to predict lower and upper quantile directly, these depend on a large data set. And in our cases, like when there's a lot of uncertainty, actually the data sets are usually very small, which is why this approach might not work. And most of them do not have theoretical guarantees. So you can't bound this error probability. When you sample those answers, you can't actually guarantee that they would represent the 95% of the things that you might see. So which is why you can't actually use that in a high stakes application, like in medical settings. So we use this framework called inductive conformal prediction, which is a method which you can add on top of any model and any distribution, so that you get these. For new examples, you get the prediction intervals such that the property of validity holds. And validity is just the property that I was just saying above. When you have a certain bounded error rate, you make sure that your actual value is within that interval with a certain probability. And this is just done by training some underlying models. So the details are maybe less important. If you would like, we have the NeurIPS conference next week, and there's also a paper that has come out, so you can actually read it, how it's done. But I basically extended this method to the time series setting, because conformal prediction generally works for one value. And in this case, we have like a time series, which we want to forecast. So we do that with multiple values in the future. And those values have to be also, there's an assumption of exchangeability. So we had to tackle these. And by doing that, we actually developed a recurrent neural network, which would output multiple intervals in advance so that the entire forecast would be held within that interval with a guaranteed error rate. And this is the proof how it works. And then we applied it to the synthetic data, where you can see with the static noise variance, you can see that the predicted values fall within the intervals in most cases actually. And when the variance increases, like you can see below, once you have like a larger base variance of the underlying time series, you can see that the intervals also get larger, accounting for that uncertainty inherent within the data. We also applied it to some medical data sets of different scenarios, including some COVID data sets. And we compared it to the dropout, which is one of the recurrent neural networks of the Bayesian framework, the multi-quantile recurrent neural network. And we saw that our method was actually the only one to have the guaranteed coverage rate. It sometimes meant that the intervals are very large, which is the case in the COVID data set. But if you care more about the guarantee rather than a small interval, you would ideally like to have both. But in this case, like if you care more about like the error rates, this is what this model did achieve. So that was a contribution of this method. And there's a lot of work on time series, so feel free to check out our website. And I don't know, Nick, if I should probably like put off the next question to the end of the discussion.
Yeah, so I believe you had a question that sort of tied together the three different areas we're discussing, and maybe if we do that at the very end. And if anyone does have any particular questions for Kamilė, I would say maybe put them into our Slack workspace. And if you want the URL for that, just look at any of the previous emails I've sent about Inspiration Exchange. Okay, so our third and final presentation is from Trent Kyono, who's one of our PhD students. So due to time zone differences, it's extremely early in the morning where Trent is, but he has kindly joined us live, but he pre-recorded his presentation for us. So let me play that first, and I'll also get the poll for Trent started up while the video is playing as well.
Hi, everyone. My name is Trent Kyono, and I'm a fourth-year PhD student with the Schaar Lab, and I have the privilege of giving you a talk today about missing data imputation and how we've addressed this important machine learning problem. Before we get started, during our presentation, Nick will have a couple of poll questions out. Let me first introduce them. The first is, do you use imputation as a strategy for handling missing data? If you answer no and use other methods, we'd be interested to hear about this. And the second question, do you think it is sensible to think of imputation in terms of its missingness types? For those not familiar with these missingness archetypes, we will go more into detail in the presentation. Moving on to our presentation, missing data is an unavoidable byproduct of collecting data in most practical domains. In medicine, for example, doctors may choose to omit what they deem to be irrelevant information. Example, some patients may be asked to get comprehensive blood tests while others don't. Data may be explicitly omitted by the patient, for example, avoiding questions on smoking status precisely because of their smoking habit, or simply misrecorded in electronic health systems. One simple approach to handling missing values in data involves removing or dropping samples that have missing values, or simply assigning them a default value, such as 0 when missing. However, as shown in the table on the right, this could be prohibitively costly when missingness rates are high and would result in only one valid sample. Alternatively, another common approach involves imputing the missing value, which is where our work focuses on. There have been significant amounts of work done in here over many years and include well-known methods such as mice, MISFORS, Canon, and even more recent methods such as generative models using GANs such as GAIN. To motivate our problem, these existing imputation methods are prone to bias due to the fact that missingness sometimes introduces bias that does not exist in the true underlying distribution. For example, suppose we have a two-variable system with x1 and x2. If either of the missingness is caused by the other variable, we have a system as shown in the DAG here. Conditioning on this missingness, R1, that we observe in the data would in fact introduce a dependence between x1 and x2 that would otherwise not be there. In general, it is important to understand that there is a difference between what we observe, the observational distribution, P of x given R, versus the interventional distribution, P of x given do R. where the latter is able to better represent the true underlying distribution without missingness. The point of this is that we can only handle missingness correctly if we understand the missingness mechanisms. That is the reason for why certain variables are missing. For additional motivation, missing data introduces a shift between the available missing data distribution and the true target complete distribution. We treat imputation as a problem of robust optimization and desire to impute features based on their causal parents. This has been shown in many prior works to minimize our expected error on a target domain where covariates may differ. We'll dig deeper into this, how we uncover the causal parents later. Next, we briefly touch on the types of missingness in terms of missingness indicators and M-graphs, first introduced by Mohan and Pearl. Take, for example, a 3-variable case with variables x1, x2, x3. They have 3 respective missing indicators, R1, R2, R3. Missingness completely at random is when the missingness between variables are independent of each other. Graphically, we can think of this as x being d-separated from r in the M-graph. Next, for missing at random, we can graphically think of this as for any missing indicator rj is d-separated from xj given the other variables in x. For all other variables, we consider this to be MNAR, or missing, not at random. Let us now present MIRACLE. MIRACLE stands for Missing Data Imputation, Refinement, and Causal Learning. This is joint work with other members of our lab, Yao Zhang and Alexis Belot, and will be presented at NeurIPS next week. Before we go deeper, it is first important to understand how MIRACLE is trained, as well as where the refinement in the name comes from. Starting with an incomplete data set, we first perform a baseline imputation using any pre-existing method to seed our MIRACLE pipeline. This baseline can be any baseline imputer from mean imputation, KNN, mice, etc. The main thing is that we do not have any missing values when training MIRACLE, since MIRACLE has a causal discovery loss term which can't have any missing values. The second step is to train an epoch of MIRACLE on the baseline imputed data. Next, we use MIRACLE to provide its own refined predictions of the imputed data. Lastly, we repeat this refinement until MIRACLE converges and stops improving. We'll first provide a high-level detail before detailing each loss. As mentioned earlier, MIRACLE requires a baseline imputer. For now, assume any baseline imputer will suffice, such as mean imputation or mice. The baseline imputation is required for the causal discovery step that requires complete data. The MIRACLE network then takes this complete data set and attempts to iteratively refine the imputed values only. We embed an adjacency matrix in the neural network input layers such that each feature is reconstructed from every other feature. Our network is optimized with respect to 3 objectives. First, to accurately predict missing values. Second, to faithfully encode the causal relationships given the underlying M-graph. And third, to satisfy a moment constraint of the missing data mechanism on the imputed values. We now dig a little deeper into the 3 components of our losses. We first discuss our reconstruction loss, which is comprised of 2 main parts. The first half is simply for reconstructing the observed features. The second loss term is for estimating the probabilities of missingness. The second objective is to ensure that the dependencies defined by F correspond to a DAG over the features X and the missingness indicators, which enforces that the learned function dependencies recover a DAG in the equivalence class of causal graphs of the observed data. As part of the learned causal graph, or DAG, we learn the missingness mechanism in the causal graph. In other words, we learn which variables cause the missingness of the missing features. However, knowing the cause of missingness can't help imputation directly. It is not the same as knowing more about the actual value of the missing features. However, the missingness mechanism provides a way to estimate the expectation of each missing feature. In the moment regularizer, we force 2 expectation estimates of each missing feature to be the same. I won't go into too much of the details here, but basically we establish an inequality in our paper that is based on the conditional dependence of the missingness patterns or mechanisms in the causal graph, and our moment regularizer enforces this. Here, we show an example of how MIRACLE iteratively refines itself in terms of both imputation quality and discovered causal DAG on a synthetic experiment. We see that as each training epoch goes on, we have lower imputation error over the baseline, as well as a more coherent DAG, as shown in the adjacency matrices over the learning curve. The true causal graph is shown on the upper right-hand side. We next perform experiments on synthetic data to examine the performance of MIRACLE under various data set sizes, missingness ratios, and feature sizes. We apply MIRACLE to 6 baseline imputations for mean imputation, gain, KNN, misforce, optimal transport, and mice. We see that MIRACLE is able to improve upon each baseline imputer in terms of imputation error for each baseline. We now show experiments of MIRACLE on real data. We perform experiments on several UCI data sets. The improvements of MIRACLE are minimal for MCAR, except for mean imputation, because the baseline imputations are not biased in the MCAR setting. Conversely, for the MAR and MNAR setting, As expected, we observe Miracle has a significant improvement on some of the data sets, and in the worst case, never harms performance. Next, we look at convergence of Miracle. Since Miracle can be used over various baseline imputers, it is important to understand how Miracle behaves or converges given different starting points. Here, we look at Miracle learning curves for our real data sets. It is reassuring that we see across each of the data sets, Miracle generally converges to approximately the same RMSE across each benchmark. Next, we look at the correlation between imputation performance and causal discovery. Here, we do not have oracle knowledge, but assume that the sparseness of the learned DAG implies a coherent DAG. We observe that Miracle has the most performance gain when fewer causal parents are identified for the missing variable in the learned DAGs. When Miracle is less able to isolate causal parents for prediction, the learned DAGs contains many spurious edges, and Miracle only has marginal improvements over the baseline imputer. Now, for some concluding remarks about Miracle, we propose Miracle, an iterative framework to refine any baseline missing data imputation to use the causal parents embodied in the estimated M-graph. Miracle learns the causal M-graph as an adjacency matrix embedded in its input layers. We proposed a two-part regularizer based on the causal graph and a moment regularizer based on the missing variable indicators. We demonstrated that Miracle significantly improved the imputations of 6 baseline imputation methods over a variety of synthetic and real data sets. In the worst case, Miracle never hurts performance, and we envision Miracle becoming a de facto standard in refining missing data imputations. We have several limitations identified as shown here, and our source code is made available in the QR code shown. Thank you for listening, and we have some roundtable questions following up next.
Okay, brilliant. So now let me just end the poll and share the results with you. And we also have Trent with us now as well. So I believe, Trent, you may want to kind of pick people who answered, I guess, either yes or no to one or the other of the questions. So if you can see the results, the first question
yes,
being
I can see them now.
Lovely. Okay.
So for question 1, for anyone who answered yes, I'd be curious to know what imputers you use, and do you think how are you specifically handling non-MCAR cases? And if not, if you aren't and you're just using it, that's also fine. I'm just curious to know if anyone can raise their hand and tell me what they're using in terms of imputation strategies.
I think we have a raised hand from whose name?
Yep.
So if you want to go ahead.
Thank you. Actually, I used the data imputation for my missing data into the multi-dimensional time series problem. So in that, I trained the bidirectional LSTMs to predict the missing data on a exact point based on the other features.
So did your data have any what would you classify the type of missingness that your data had?
It's a time series data, like it's very, very big data. And the thing is, there is one feature, many features which are missing data, like some chunks are missing at that time. So I solved by training the simple bidirectional LSTMs to learn from the previous timestamps and just predict the next one is just similar like forecasting. So I added the forecasting into my data, and it worked pretty well actually. So I think my case is not related to the health; it is something very, very different. So
yeah, thank you for sharing. That's awesome.
So I think that's pretty much all the hands we have raised at the moment. Hussein, I assume your hand is still raised just because he had it raised before. So I think, Kamilė, I think you had a sort of final wrap-up discussion that sort of touches on all 3 of the topics that we talked about today. If you want to go ahead and introduce that, and then we'll wrap up.
Yes, I just wanted to ask more like about how to, if you could all be like very creative and like maybe think offline in the future, how could all those techniques be in a way combined? Because there's a lot of, there's the uncertainty related to missingness, because like there's uncertainty in predictions because of the missing data. There's also uncertainty in when you do imputation, well, as Trent presenting, there's uncertainty in like whether the values you imputed are correct. So there's a lot of things that are kind of uncertainty that are tied to uncertainty, but in very different ways. And I was thinking, like, could this all be kind of combined together in like a single framework where kind of you have some requirements on how much uncertainty do you want to have, or you have a method that could tell you how uncertain it is in imputing certain things, and then in predicting certain things because there's missing data that it imputed. So if you have any thoughts on this, I understand it's a very difficult question, but in case it is, then you can also think about it in the future, and maybe like we have another session on this. So that would be interesting.
Yeah. So if there is anyone who has any thoughts on that, please raise your hands. I'll give it just a few seconds, and in the meantime, I'll just get ready to wrap up anyway, since we have actually reached the exact 1 hour point pretty much. We do have a raised hand. We have 2 raised hands and 1 thumbs up. So I guess we just go in order. I think I saw Chang's hand come up first, and then I guess we go to Shinkai.
Yeah, so mice, right? The imputation scheme, mice, multiple imputation. So is it like kind of doing that? It's doing imputation as well as considering some of the randomness, so that it's generate multiple repeats of the imputation. But my question is, if we have a framework that is doing imputation as well as uncertainty, like how do you use it? How do I use results coming from a imputation scheme that might gives me confidence interval as well as like multiple results of the imputation? So yeah, so I've been like thinking similar questions, but I'm just kind of curious, how do you actually use it if you have such a framework?
Well, unless someone else also has thoughts, because it has to be kind of an inspiration exchange. I think it kind of all ties together as well, because like if you're very uncertain in what you're imputing, probably very uncertain in what you're predicting. So I think that kind of also, I guess, carries over to your future tasks. And I guess so it's kind of used in that way.
Right, so in the future task, I have prediction, uncertainty from the prediction itself, as well as from the imputation, maybe. Is that what we meant? Oh yeah, that's interesting. Thank you.
And then I guess if we go to Shinkai, and then maybe finish up with Josh.
Hello, can you hear me?
Yep.
Yep. So I was gonna mention the same thing, the multiple imputation, because which was specifically designed to evaluate uncertainty from imputation itself, right? So if we can do that, then on each imputed data set, we use your uncertainty method, conformal prediction, and we get like a confidence band or whatever, and then pull the results from different imputed copies of the data, then would that be enough to give as an overall uncertainty quantification? That's just my thought.
Yeah, anyone else?
So I guess the last person we go to maybe is Josh, and then I think as we've we've hit the time limit, we'd probably have to wrap up after that. So Josh, if you want to go ahead.
Sure. I don't know if this, I was just trying to think this through, I don't know if it makes sense, but this kind of takes into account the imputation and the uncertainty aspects. So sorry, not the less the synthetic, but I was wondering if I was trying to understand whether, I was trying to think whether imputing, like how you would define uncertainty, and I was wondering whether it would relate to the bias variance trade-off type thing. So like if you impute, do you reduce variance and then increase bias? And if you don't, do you increase variance and reduce bias? I'm trying to think whether that makes sense or not. I was just trying to think how you might balance it, how you might quantify what to do. I don't know, does that make sense, or am I talking rubbish?
Yeah, I think that's something for me to think about as well. So
okay.
now that's I guess that's the purpose of the session, to inspire all of us to think.
Boris, I think you're unmuted. I was just wondering if you wanted to add anything or.
Yeah, going back to the question of the previous question, I think the multiple imputation is actually not required to do conformal prediction. So even if you do single imputation, you can actually already use the conformal prediction method based on these imputations and still get conformal prediction. So that doesn't, however, so the multiple imputation only helps you to give uncertainty estimates in the missing values themselves, whereas the conformal prediction gives you uncertainty estimates in the downstream prediction. So that's, I think, an important distinction. And you could also maybe do both multiple imputation and then on top of that conformal prediction. That would be a little bit more difficult. I don't think anyone's done that. Could be interesting, but not necessary for conformal prediction.
Yeah, I think so. When you do conformal prediction on a data set, you are conditioning on that imputed data set, right? Then you're not really taking into consideration the uncertainty induced by imputation. But if you repeat that process multiple times, then and do multiple conformal predictions, then I think the uncertainty is baked into all those confidence bands from conformal prediction, right? Then when you either average those confidence bands or do some summary statistics on them, then you are taking into consideration the imputation, right? Uncertainty due to imputation. That's my thought.
Okay, brilliant. Sorry, I think I kind of have to get to the point of wrapping up, I'm afraid. So I just wanted to, before I go, leave you with a bit of information about what we're doing next. So our next session will be in early January. We've penciled in January 7th, and it will be on ML and AI for organ transplantation. So a somewhat more kind of specific focus that time. And this session, if you do want to rewatch it, will be on YouTube soon. But in the meantime, I'd like to remind you that you can catch us at NeurIPS. So we have 14 papers, each of which comes with a poster session. And we also have 2 workshops at NeurIPS. And if you want to find details on that, you can just go on our website. And it's basically the top thing we have in our most recent posts there. Also, again, if you are interested in joining the lab as a PhD student, you can submit an application on the Join Us page, which you can again find right there on our homepage. And also, just a quick reminder, I introduced this last time as well, but last month we held an open house where we covered 10 topics kind of in a very high level manner with some very short presentations on 10 of our key research areas. If you want to have a look at that, it's all available to be watched at your leisure. Just find it again on our homepage. And in the meantime, if you do want to stay up to date with these sessions, you can visit the dedicated page for Inspiration Exchange, which is on our website if you just click engagement sessions, or just follow the URL that you see here. And also, of course, we are trying to build a community. So please, if you have any friends or colleagues that you think might be interested, please just share these sessions with them and let them know about them. In the meantime, we very much look forward to seeing you in the new year for our session on ML and AI for organ transplantation. In the meantime, please take care, stay safe, and thank you very much for joining, and all the best.